Hello, everyone. Welcome to DeepLearning.AI's online mini event series for AI for medicines, the learner community. My name is Jan Jitse Venselaar, and I'm very honored and excited to be your guest speaker today. I'll be speaking for the first 10 minutes, and then I'll be answering your questions that you posted on Slack for the rest of the time. And don't forget to post any comments and questions and upvote questions on Slack. Great. So let me share a little presentation I made. Yes, here we go. So that should be now visible. So I'll be talking about using machine learning for monitoring MS, multiple sclerosis patients. So first, a little bit about myself. So I have a background in pure mathematics. I have a PhD on non-commutative geometry, which has absolutely nothing to do with machine learning or AI, but it was very cool to do. So I learned machine learning through Andrew's original book, on Coursera, and doing some projects, mostly for fun. For example, I tried to predict the outcome of the Eurovision Song Festival, which was a challenge because, it didn't take into account any of the quality of the singing. And I did a lot of other courses on DeepLearning.AI and course providers. Then I worked in the semiconductor industry for 4 years. I was an engineer, mostly doing semiconductor metrology with machine learning, developing new ways of nanometer shifts, of detecting nanometer shifts of computer chips while they're being made. So that was quite interesting. But then I decided to work for another type of another type of business. So I'm working currently on machine learning in healthcare. So using machine learning to improve healthcare. So this is very relevant, I think, for the course at hand. And this is what I'll be talking about now. So just a small disclaimer: any opinions and statements are my own and not for any of the companies that I am or was affiliated. Okay, so what do we want to do? So we want to monitor the progression of multiple sclerosis, MS. So what is it? So MS is a chronic disease where nerve cells in the brain and the spinal cord, so the central nervous system, are damaged by the it's an autoimmune. So the immune system attacks the central nervous system, and that leads to deterioration of the control of the muscles. So at first, patients will suddenly drop over or fall and they will have more and more trouble walking. And it's mostly first diagnosed at people between 20 and 50 years old, and it's a very long-term disease. So people live decades with it, but progressively becoming worse. And this is where the machine learning comes from. So what happens is that so the disease has different stages. So there's the progressive relapsing. So it generally becomes worse, but there's some relapses, what are called relapses. Then there is a secondary progressive. So there's a few relapses. In between, it's steady, and then it becomes worse and worse again, and it becomes, at the end, it becomes progressively worse. There's a primary progressive and relapsing remitting, which is maybe the most famous one of MS. So you have an attack, you go back, most of the same level, but a little bit worse. And then you have an attack, and you go back to the same. So these are different types of stages, and they can go from one stage to another stage. Now, what happens is that depending on the stage, different medicines, different mitigations are provided. So maybe you get a walker during a certain stage. Maybe you get a different type of medicine, which actually are quite effective at suppressing the symptoms. But it depends on which stage you're in, what medicines you can get. And So you want to know, and patients themselves want to know, where am I? In which stage am I? What kind of things should I do? What shouldn't I do? That sort of thing. So that's very, it's very interesting for the patients, the doctors, and other also pharmaceutical companies want to know, so they can provide new medicines. So you want to know how this is done, and for this, well, you need sort of continuous monitoring of how the patient is progressing. So what can we do there today? So currently we can, well, you can do an MRI scan of the brain. It's expensive. Yeah, you can only do it so often. So what you look at is black or white spots on the brain. So these are called lesions or plaques. They're the areas that are damaged by the immune system. So this is expensive, and it's quite a burden on the patient, actually. So it's non-invasive, but still you sometimes have to put in a contrast liquid. You have to lie still in this MRI machine for quite some time. You have to go to the hospital. If you have trouble walking, this is a big step. There's also the option to ask patients to come to a clinic to do some cognitive tests, to do a walking test, see how far you can walk. This is of course done, and you talk to your doctor, but this takes time, and it's only a snapshot. It's only a snapshot in time of how you are doing at that time. So people are looking for some continuous monitoring. So in the Netherlands, where I'm based, so the frequency of these visits for MS patients is around 1 to 2 times a year. Doctors try to get around this by having a questionnaire about, hey, did you have any relapses in the past months? But people are this is typically very subjective. Yeah. So what can we do otherwise? So this is monitoring. So everybody nowadays has a smartphone. You can try to have some smartphone monitoring your health. Just not anywhere here, but the implementation, well, there's some. So yeah, this allows for continuous monitoring. It's objective. It's very low burden for the patients, and it gives you fast feedback. So you can also say, okay, try to change your diet and see how that affects your ability to walk. Or you can try a new medicine and get a feedback of how it's going within 1 or 2 weeks without going to the clinic. So this is very interesting. Also, what I heard from patients is that they like to monitor themselves, so they can see for themselves objectively how they're doing. Are they doing step before, or are they not progressing? That's very interesting for them to know. Well, the challenge is, of course, to make this this monitoring good enough. So what are the options here? So you can have a questionnaire like you have in the clinic. So how do you feel? Are you tired? This is, of course, very subjective, but if you do it often enough, you can try to see a trend. There's a response test, which is called the symbol digit modalities test, the SDMT, where you basically have you see a symbol on a screen and you see a list of symbols with numbers, and then you add, well, you press the right number. If you say the right number, depending on how fast and how accurate you do that, you can sort of measure the response, your response time, and how tired you are. Then there's a new idea is you use the phone on your or the camera on your phone to track how tired. This is very, of course, a very interesting idea where a lot of machine learning is involved. But I'll not be talking about that today because, well, we saw that it was very promising in lab environments, but typically. What we saw is that the cameras, the front-facing cameras are on the newer phones are good enough, but on the older phones, what we saw a lot of patients have older phones were not good enough, and it's very dependent on the light. For example, if you have glasses and there's a little bit of light falling, reflecting off, you can't track the eyes. So that's very yeah, and then it becomes a burden to the patients. They have to take off their glasses, look around. So, yeah, it's a lot of things. So what I'm talking about is a seemingly very simple thing. Is so a walking test. So how far can you walk in a certain time? So typically this is done in certain step time periods, like 2 minutes or 6 minutes. There's even a 15-second test, but that's too short to be very effective. Now, so what I worked on was a 2-minute walking test. So that's measuring how far you can walk in 2 minutes. Now, it's very simple to do this in principle. So you just take the GPS locations of your phone and add them all up. Now you can see that in this picture, sometimes it's simple, sometimes it's not so simple. So here you see an example of well, what probably happened is there was some reflections of the GPS signal on some high buildings, high rises. Now, this meant that, well, we should be able, we can throw away this measurement. So this is not usable because, 2-minute walking and then there's a jump of around 20, 30 meters. Well, typically we see that people walk around 150 meters in 2 minutes. If you have an error of 20 meters, it's unusual. Also, one of the other problems is that you need to go outside. So if you're a mass patient, that can be a burden. If you walk 20 to 50 meters in 2 minutes, think about it. Going outside is quite a fatigue-inducing thing. Now, also with the current lockdown, you don't want people to go outside willy-nilly. So what we did was the following. So we used machine learning for better monitoring. The idea there is that we use the accelerometers and the gyroscope sensors on the phone. Really a classic ML problem. So we have some input data. We know is related to the output data, which is, target data, so how far you walked. And you try to match them with the neural network. So the target data is, it's quite fun to see how this was gathered. So you have people walking with 4 phones, 3 people abreast, and then a walking wheel there measuring, okay, how far we're walking in 2 minutes. And then all these different phones gathering all the data from left to right pocket, different types of phones, different types of surfaces, different types of people, of course, walking, different heights, all this sort of thing. And then, you train a machine learning model to predict the distance from this time series data. So you have quite a lot of data in principle per measurement. So you have 2 minutes. It's the phone measures this thing at 100 hertz. So you have for the gyroscope and the accelerometer, you have 3 dimensions each, so X, Y, Z. So you have 6 times 12,000 points. It's quite a lot, quite interesting. So let's see. So what we did there, well, in the end, so the network architecture we came up with, so we have the input time series. Of course, the time series is normalized, so mean subtracted, standardized, and then we had a feature detection layer. So in this case, it was, well, I came up with a 1D convnet for this. You could also do a short-term Fourier transform and then do 2D convnet on that. Typically, we have 1 or 2 layers of feature layers. So first 1D convnet, then another 1D convnet in my case. And then there was an accumulation layer, which was either some simple RNN or an LSTM layer, or even a normal dense layer would work. And then there was a regression output. So we trained that. The machine learning in principle was very simple. You just have to come up with the right network and the right parameters to make this work. And of course, gather the data, which was actually one of the harder parts to do. And I'll come back to that. in so how did we set up the architecture? Well, it's mostly so we did everything in TensorFlow. Because then we could easily put all the training also in the cloud. So we used Kubeflow for that, which is a product to well, it's I think a Google project to make to do things easily in the cloud for machine learning. So this is a typical architecture that you then see. So this is an extract, transform, load plus a machine learning plus a validation step. And each of these is then a separate Docker container where you do this, where there's a small Python script which basically loads in the data, transforms it, does some stuff on it, and then writes it out. It takes a few parameters, and all these parameters are safe. So this is very important because what I talk about at the end is you have to you have to validate, and you have to show to some medical validation board that what you did is actually that's a very interesting proposition for machine learning because typically, well, you only have to show internally that it works, but not how it works. How here you have to show how you came to the results, and you have to document. So we put everything in Docker containers, put it online, train it there using TensorFlow, and then well, we also use a hyperparameter optimization framework to tune the hyperparameter. Because if you, well, especially if you work in the cloud, you can't just all the time upload new Docker containers. Well, it's easy if you can do that automatically and automatically tune your hyperparameters. So I really like it. This Optuna framework. There's other parameters. There's I think Amazon has a product for that as well, SageMaker something. And also I know there's a hyperparameter optimization Python package. But these type of things are, well, they're very simple to set up, and they take a lot of the pain out of the tuning of the hyperparameters. You can just run it overnight. Of course, it will cost you if you do it on the cloud, but you can just run it overnight, and it comes up with a quite reasonable set of hyperparameters. And then for deployment, so the model is put in a Docker container, sent to the cloud, and then the data from the smartphone app is also sent to the cloud. There, the model is applied, the feedback is sent back to the user, stored also in the cloud and on the phone, so that the user, the patient, can see it directly. So how far did I walk today? How far did I walk yesterday? Am I progressing? Am I regressing? That sort of thing. And also the general practitioner, the doctor, can also see it. The doctor typically has a dashboard that they can then look at if they see the patient coming in. So, yeah, how did you do last 6 months? Okay, I see that you won. Very well, didn't seem to get any worse, so that's good news. Yeah, so this is the general setup. So some of the challenges we faced. Oh, I have to say, I didn't do this all by myself, of course. So my colleagues, and especially I want to call out Amkar, Leila, Pim van Oorschot, and Frank Dorses. Yeah, in setting this all up. Actually, they did most of the work, I would say. So what are the main challenges? First, from a machine learning point of view, actually, even with this setup where we had 3 people working at the same time with 4 phones each, we had very little training actually. So I think in the end we had like 16. Well, no, we had around 400 individual so 400 training time series, and we had to put quite a bit aside for validation, for the medical validation. They set up other rules then for machine learning. So we solved that to using a lot of augmentation. So we had a lot of jitter. So we added some noise on top of the time series data. We rotated. So we did. So one problem was that our phones, well, you put your phone in one way. You put your phone one way in the pocket, and maybe somebody else puts it in the other way. Well, you can simulate that. You can also simulate all other kinds of rotations. Well, rotation through time, it sounds a bit amazing, but what I mean here is that so you cut off somewhere, you have the 120 or the 12,000 points, you cut them, let's say midway, and then you so you cut them up midway, and you glue the first part to the last part in another. So that should give you the same outcome. So it's a valid augmentation, and in that way we extended the amount of training. Actually, we also found that it's hard to get the relevant training. So, of course, when a healthy person is walking for 2 minutes, typically they walk a lot further than the EMS patient. So we had, at some point, we realized this, and so we started walking slow to get some more data from slow walkers. But the question was how representative is this data for EMS patients? So that's still a bit of an open question, because it turns out that it's well, there are all kinds of legal considerations if you want to gather data from patients. I'll talk about this in the end. So what we did is we rebalanced the training set using oversampling, one of the standard techniques, but sometimes simple techniques are very effective for this sort of thing. So we looked at, we bucketed the walked distance into buckets, like 0 to 40 meters, 40 to 80 meters, 80 to 120 meters, and we picked a lot of we oversampled from the shorter distances, so they're as well represented as the longer distances in the and then also there was a lot of non-uniformity in the data. So especially if you gather the data on an iPhone or Android phone, there's quite a bit of difference in how everything is measured. So that's was a bit of a problem. So we luckily found a software library called Sensing Pitch, which can be used to at least get it in the same format. And then also what we saw is that we just have to normalize the data, so it was exactly 12,000 samples. So we either cut it off or we extended with zeros. And, that was solved enough. And then we had many different architectures. There's of course an infinite number of network architectures to consider. And there was not much literature on this type of problem. So using a time series data for this sort of for regression. So in the end, what we did was we took some information from there was a paper on the deep sense network, which is gait detection, so how people walk, walking, sitting, running, that sort of thing, based on this type of data. So it was a classification problem. And then in the end, we took some information from that type of network, and then we made it into a regression problem. And that was also when the hyperparameter tuning came very helpful, because that can also train different types of networks in the same. So finally, I want to talk a bit about what are the challenges if you're working with medical data instead of just any other data set. So if you're, let's say my example would be semiconductor industry, if you're looking at chip data. So it's not, medical data is a bit special sometimes because, I don't have a medical background. And you have to say what is medically relevant. And I don't know, typically, I can have an idea, but that's not what doctors want to see typically. So you need to work with the clinical experts, with the doctors, to say, okay, we can measure this. Is this important to you? We could also, I mean, we could have measured the maximum speed that each person would, but typically doctors were, yeah, a bit conservative. So they want to try test method. And in this case, the 2-minute walking test was very relevant. You also have to see what is allowed. So you can't just gather all data from all patients and then afterwards say, okay, let's try. Can we detect this? Can we detect that? It's that's a very typically not allowed. So you're not allowed to go on a fishing expedition to data mining to see what you can do with your data if the data is from persons. You have to tell them beforehand, I'm going to do this and this with your data. And then you're not allowed to do anything else. And it also has to be a usable app. So you have to talk to UI UX experts to see, what I'm proposing is this actually do for the patient. So you can't just tell them to go running. Because MS patients, you can tell them to run. That's just dangerous. And they're also not because they have problems controlling the muscles. You can't ask them to do very fine control of the app. So you have to work. So some terms that I learned over the past few months when I was working on this was what is the minimum detectable change? So what can we detect actually, and what certainty can we detect a change? So for example, if you one day you detect a 50-meter walk, and the next day you see that the patient is doing a 40 walk according to the model, is that a significant change? You need to be able to quantify that, because otherwise, so the doctor is not going to do that for you. They don't know how your model works, how accurate and how precise your model is. So you should be able to tell that to the patient, to the doctor. Is this actually a significant change? But for that to know, you also need to know what is the minimum clinically relevant change. So when is a doctor getting worried? Because maybe 50 meters, 40 meters the next day, there's just a normal variation of a person. So one day you maybe it's raining, maybe you feel a bit tired, maybe you had some leg problem that day extra. It's just a normal change, maybe. So you should be able to detect that as well. So what is a normal variation? And from what point onwards do I need to start worrying? And of course, it would be very, it's actually a requirement that the minimum detectable change should be lower than the minimum clinically relevant change. Otherwise, your model is not going to tell you much useful. So if you have a minimum clinically relevant change of let's say 10 meters, but the minimum detectable change is 20 meters, you're only going to see very large changes. And actually, you don't want that. And then, so I'm based in Europe, so there's all kinds of rules, CE validation rules. In order to advertise your app for medical purpose, you need to have a whole bunch of rules that you apply. So, for example, you need to show documentation that your app works as intended and is not dangerous. You need to every change you make in your app, for example, if you just change your model parameters because you think it will be better, you need to update your documentation. And these rules change also. So there was going to be a big rule change on the 26th of May this year, but luckily that's now postponed because of the corona crisis. And these rules, they're really, well, I found them really hard to follow, but luckily there's a lot of experts on that. But these experts don't always understand machine learning. So they try to, but they're a bit scared of having, okay, you have a black box model. So what is it detecting, and how can I trust it? So that's for that thing you need typically to gather a lot of data. Yeah, and then so the data gathering. So patients are typically protected group. So you can't just say, I'm going to find 100 patients and give them this app. That's just not allowed, at least here in the Netherlands. Okay, I see you already talked for quite some time, and I see there were some questions. So I see one from Asiel Goldschmidt. So if I understand correctly, the training set is people walking in a certain distance and the accelerometer data accumulate. Why not instead use the glitchy GPS data together with the accelerometer to correct the glitches using an ML? That's a very good question. I think it's a very worthwhile approach. So I worked on this now for the past 4 months. We had originally a deadline at the 26th of May, and we thought our first approach using just the accelerometer data was the most promising one to get this working in time. I think stitching together GPS and ML data is, I think, the accelerometer data is a very promising thing. Yeah, I think it could work. Yeah, one thing is that the GPS data and the accelerometer data is from it has a different time frequency. So the GPS data is typically once per second. The accelerometer data it has a frequency of 100 hertz, so it's 100 times a second. So that's a bit, you have to stitch them together in a proper way. So there's a question from Nivedita Bailak. I hope I pronounced it correctly, but otherwise, sorry. So how did you do external validation of your model? What exactly is the regression output? What information is fed back to the patient and the GP? So the first one is the external validation is we had a group of measurements from people that we didn't consider in the training. So we had a group of test persons that did a lot of walking, and we validated the outcome of the model for them with the actual distance walked. So we were very clear that this was data from test persons that were not seen. And what exactly is the regression output? So the regression output was meters walked in 2 minutes. So we had that was the target data, and this was also the output of the regression model. And this is the information that was fed back to the patient and the GP. So we were not in general making statements on how the patient was doing. We were just saying, okay, on this day you walked this amount. And by the way, our precision is what we say, or the minimum detectable change. When is it a significant change? Is this amount. But that was all we were saying. So really, it's really important here to have a human look at this data and say, okay, I walked very slow that day, but that was because it was raining, or I was very tired that day. Oh, yeah, or I walked very fast that day, but that was because I was walking with a friend and I had to keep up. So it's very important to have a human in the loop. Yeah. Then there's a question from David. So how did you make the switch from the semiconductor to the medical image analysis? Yeah, that was so they're very far apart in some way. So yeah, I didn't do much. So it was both actually, I see it was both machine learning, just in a different field. And I was lucky to come into a company which had a lot of expertise on the medical regulations, a lot of expertise on the medical stuff, and some machine learning experience. So there, I was able to get up to speed relatively quickly by just talking. Okay, what is this medical? What is different in medical work compared to semiconductor? Yeah. It wasn't, yeah, actually, yeah, it was not much of, so I didn't have to do much, just apply to a few jobs and find the right fit. I guess I was very lucky at that time. So there's a question from, there's an earlier question, actually, let's not forget that, from Satvik Surasity. So that was, how exactly can I use a neural network autoencoder? Yes. How can I use a neural network autoencoder for drug discovery? For example, how can a neural network discover drugs, and how does the process work? Pardon me if this question is simple. Well, actually, I don't think it's a very simple question. So I'm not an expert here. But I think it's, yeah, so let me try to venture a guess. So there are two things here. What I heard is that, so one thing is, so there's a lot of machine learning and AI going on now to faster see how proteins are folding, and see if we can speed that up using AI machine learning. That's a very interesting approach. What I think is on the short term simpler to do, and might also give big gains. Look at a list of already relevant or regulated medicines, so medicines that are known to be safe, at least in certain doses, and see if they have other effects that can be used for for new diseases. And there's a lot of AI work, I think, ongoing. So, for example, scanning the literature for relevant effects. For example, to see all the side effects. Maybe one of the side effects is actually a good one, or seeing, okay, similar medicine here, similar structure here was deemed to be useful, and we have this medicine that actually is already, cleared to enter the market for a different type. Well, then it's relatively easy to see that medicine, test if that medicine also works for this. So I think AI and machine learning is very useful in that regard. For the protein folding, I think it's more a substitute right now, or in addition to brute force computing. That's one part. And I don't know if there's an autoencoder that does this or not. I'm not an expert there. So there's a question by Lei. So is this kind of like anomaly detection on time series? Well, yes and no. So anomaly detection, well, on time series data, yes. But what we are looking at is the whole of the time series data and then attach a number to that. I think typically anomaly detection looks at intervals and then see if those intervals are similar to what you've seen before, yes or no. So it's more, anomaly detection doesn't look at the whole time series as a whole, typically. And this is a regression problem, not a classification problem. And actually, anomaly detection is I think typically much harder, because the problem with anomaly detection is that you typically have very little training data for the anomalies. Hopefully, otherwise it won't be anomalies. So yeah, there's a lot of extra tricks involved, I think, in anomaly detection. But yeah, so processing the time series data, of course, is simple. I see that Greg Casey has a very interesting talk about very interesting link about the testing using AI to improve or find new drugs. Okay, I think I'll. So it's well. I think I'll answer one last question, and then yeah. So this is by guide Sankar. So thank you for your presentation. What are future improvements in case this model meets expected target? So possible future improvement that I think, well, of course, you want the model to be more precise, ever more precise, but at a certain point, you're meeting the target, so you should look into that. I think making the model more flexible. So now it was really focused on the 2-minute walk, but maybe for another group of patients, you want a 3-minute, 6-minute walk. You want to go to a type of model that is more fine-grained. For example, okay, this was this distance in 2-minute walk, but also the top speed was 5 meters per second. It's quite a lot, but that sort of thing. So more output parameters and a more flexible input. That would be the future improvements that would be nicest to have. I hope that answers your question. I'll be looking at the Slack channel to see if I can do some questions there. Answer them later. And yeah, thank you for joining all today. I hope you enjoyed it. Find it very exciting. So yeah, for the questions that I didn't have time to answer, I'll leave comments on Slack. If there are more questions, please ask them. And the recording of today's event will be available on YouTube on the same link if you want to rewatch it later. Yeah, thanks for watching, and looking forward to seeing you at future events. Bye.